What's up, everyone? Terry here, the Brainy Nerd Tutor, and we're going to go over this problem here where we're going to estimate the molecular mass of an unknown gas as accurately as we can, given this data here. Now, we're given data on pressure and density, and we're varying the pressure and taking measurements on this gas, and they're all being performed at 300 Kelvin, and based on this pressure versus density data, we want to know the molecular mass in grams per mole. Now, we want to do it as accurately as we can. And if we look at this, because we're changing pressure and density, we can't just average our data here. So we're going to fit this to a line. So I'm going to graph this in Excel. Pressure is so this was 0.4 atm, 0.8, and then 1 atm. And then the density was 1.512, 3.088. 1.512, 3.088, and 3.900, 900 here. And we have this straight line, and I don't know why there's a linear equation already here. That appears to be a straight line, I should say. And let's put a linear fit and see how it looks. So we're going to add a linear display equation on chart. And if we look at this, it's really good. It's a really good fit, isn't it? It's the r squared, which tells us how good of a fit it is, essentially, without getting into statistics. 0.9999. You can't really get much better than that for experimental data. But there is a y-intercept here. There is an intercept at density. And we want to do this calculate this as accurately as possible. And since this is a real gas, we can't assume it's an ideal gas. It won't behave as an ideal gas perfectly, but it does in the limit of zero pressure. But in the limit of zero pressure, we have a negative density. So we can do a better fit on this. So let's get rid of this linear trend line, and let's add a polynomial trend line, which is what we often do with real data. So we'll add a polynomial. Now, we can include as many terms as we want. Just do 5 to see how it looks to start off with. And when we won't set the intercept, we don't want to force it through 0, 0. We want to see it naturally go through 0, 0. So we'll display the equation, r squared on the chart. And make this good. So a little bit bigger here. And I'll add a few, I'm going to add a few more decimal places here. Format trend label, add some decimal places. Say 5 should be way more than we need. Okay. Perfect. So with 5 decimal places, we now have this fit to a curve that's going through 0, 0. So in the limit of zero pressure, we have 0 density, which is what we want. We don't have a negative density. So we can model this real gas as an ideal gas in the limit as pressure equals to 0. And this is our equation here to model it. So we have, now the y it's not really a y, it's really d for density, and our x-axis is pressure here. And this is the equation that we can use to model the behavior. So density equals 0.2 p squared plus 3.7 p squared. So we're going to go back here, and our density equals 0.2000 p squared. Is it plus? Yes, plus 3.700, and there's 0. We'll do the sig figs at the end. And then essentially the intercept was 0 here, minus 0 essentially. So we just won't include that here. So now we're modeling this real gas. And in the limit, I'll write it out here, in the limit as p goes to 0, real gases model ideal behavior. Which means even though we know nothing about this gas, we don't know what equation of state it would model it the best. We're doing a polynomial fit, and then we're going to say that in the limit as p equals 0, we can use our friend PV equals nRT here at p equals 0. So that's what we're going to do. Now, we don't have density in this equation here, and we don't have molar mass. So we need to do a little bit of algebra to get density and molar mass in here. We know what density is. This is a mass density because it's in grams per liter. So density is mass over volume. And our molar mass, or molecular mass, is mass over moles here. So why don't we substitute, we'll solve for moles here. Moles is mass over molar mass, and we can bring this into our ideal gas equation. PV equals, the moles is mass over the molar mass times RT. Great. And now we want to solve for the molar mass, right? And we also need to incorporate density into here. And density is mass over volume. But right now we just have a mass over here, and we have a volume over here. So we're going to solve for molar mass. And, well, maybe I'll just do that right now. So molar mass, multiply both sides by molar mass, divide both sides by PV. So we have mRT over PV here. So this will help us solve for molar mass, but we need to get density in here. And if we see density here is mass over volume, and we have a mass over volume. So we can substitute mass over volume in. We can substitute density in for mass over volume. So this becomes density times RT over the pressure here. Now in the limit of zero pressure, this denominator goes to 0, and the numerator goes to 0. They both go to 0. But we can calculate the rate of change at which the density over the pressure goes to 0 based on our equation here. We can take the derivative of this, derivative of density with respect to the pressure equals, and we'll do the power rule here, so 0.4000 P plus 3.7000, another power rule. So this is the density here. And this d over p, this rate of change, is equal to this d over p here at p equals 0 here. So we can substitute this in at p equals 0. Now at p equals 0, this just becomes 3.7, right? Because p is 0, so this term 0 is 3.7000. And we should put units in here. So density is in grams over liters, and the pressure is in ATM. Got to make sure our units work out. And now we basically have everything. So we have the density over the pressure, that's the slope here. We have R is just the gas constant, and we have the temperature of 300 Kelvin. So we can literally just plug it in. Molar mass equals, so this d over p is, oh, maybe I'll use a different color. Maybe I'll use pink. That's nice. D over p is 3.7000 grams over liters all over ATM. And we need to choose the right R, the R that has the right units, Now our density over pressure, that has ATM in it, it has liters in it, so we'll use the 0.082061, and that's ATM liters per mole Kelvin. Temperature has to be in Kelvin, and our temperature is 300. It's already given to us in Kelvin, so that's nice. That's a 0. Let's change that here. 0.0 Kelvin, and that's it. Yeah, so we got this one, R and the T, so we'll plug that into our calculator. 3.7 times 0.08206 times 300. So that looks good there. Okay, there we go. So 91.0866. 1, 2, 3. I think we only have 4 sig figs here. 91.09. So 91.09. And do our units check out? ATM cancels, liters cancel, Kelvin cancels, and all we're left with is grams over moles here. So grams over moles. All right, so there's the molecular mass, modeling the gas as ideal in the limit of zero pressure. Hope you enjoyed it. Cheers.